De Broglie hypothesis. In this lecture, I will teach you the super easy concept of de Broglie hypothesis, which many students are not completely understanding. Firstly, let me teach you the wave-particle nature of light. We already know that light behave like a wave and particle. For example, diffraction or interference prove that light behave like a wave. It has all the properties of a wave, like frequency, wavelength, and speed. Secondly, photoelectric effect shows that light behave like a particle. According to Einstein Baba, light is made up of photons, which are energy packets. When these photons hit the surface of a metal, after collision, they eject or remove an electron from it. It shows that light also behave as a particle. So we say that light behave as a wave and light behave as a particle. Now according to these facts, we say that all electromagnetic waves behave like a wave and a particle depending on experiment. Let me repeat it. All electromagnetic waves behave like a wave and a particle depending on experiment. Secondly, you should also learn or understand the wave properties of light. For example, consider this light wave. We already know that the maximum upward displacement from the mean position is crest and the maximum downward displacement from the mean position is trough. Now if I say wavelength of this wave and frequency of this wave, can you understand it? Well, wavelength is the length of consecutive crest and trough. For instance, this is the wavelength of this wave and it is represented by Greek letter lambda, while frequency is the number of waves produced in 1 second. Remember that speed of a wave or light is equal to wavelength and to frequency, or c is equal to lambda and to f. So note it down this equation. Here, let me teach you one big problem of classical physics. According to Einstein Baba, light also behave as a particle. In physics, we say that when a particle is moving, it possesses some sort of momentum. For instance, if this ball is moving, it possesses some sort of momentum. Its momentum is P equals mn to v, where m is the mass of the ball and v is its velocity. Now what about the momentum of the light? Well, you may say that momentum of the light is also P equals mn to v. But this is wrong, because the rest mass of the photon or light is zero. We cannot use this equation. Thus it is Einstein Baba who gave us the equation of momentum of light. In his special theory of relativity, Einstein Baba states that the momentum of light is P is equal to h upon lambda, where h is the Planck's constant. Its value is 6.626 into 10 to the power negative 34 joule second. So the momentum of light is P equals h upon lambda. So note it down this equation. To conclude all these concepts, if I ask you to write the equation of wavelength of light, you must write c is equal to lambda into f. Similarly, if I ask you to write the equation of momentum of light, you must write P equals h upon lambda. Thus note it down these two important equations. Now what is de Broglie hypothesis? Well, in a short sentence, it is wave-particle nature of a particle. In our previous slides, we have already learned that light behave like a wave and particle. Now in 1924, a French scientist, Louis de Broglie, states in his PhD thesis that any particle like electron also behave like a wave and particle. Let me repeat it. Any particle like electron also behave like a wave and particle. For example, if I take this electron, it can behave as a wave and it can behave as a particle. It means that the speed, wavelength and frequency of this electron is connected by this equation V is equal to lambda into F. Remember that wavelength of electron is called de Broglie wavelength and the wave of electron is called de Broglie wave. Secondly, what about its momentum? Well, de Broglie states that its momentum is the same as that of light. Let me repeat it. De Broglie states that its momentum is the same as that of light. And we know that the momentum of the light is P equals h upon lambda. Thus remember that using these two equations, we can calculate the wavelength and momentum of electron in quantum mechanics. Now overall, de Broglie states that every particle in the universe can behave like a wave and particle depending on experiment. For example, consider this moving ball. It can act as a particle or it can act as a wave. Consider this moving car. It can act as a particle or it can act as a wave. And consider these moving balloons. They can act as a particle and they can act as a wave. Now you may be thinking that why we cannot observe the wave motion of these objects. The answer is simple. The wavelength of their motion is extremely small that we cannot detect them. That's why we cannot observe their wave motion. So remember that it is due to small wavelength that we cannot detect the wave motion of these objects. Here, let me teach you one important question. Who experimentally proved de Broglie hypothesis? Well, in 1927, Davison and Germer performed an experiment where they fired electrons at a crystalline nickel target. They proved that electron can diffract like a wave. Their wavelength of the electron exactly matched the de Broglie wavelength. So de Broglie hypothesis is proved 100% right. For this achievement, de Broglie was awarded Nobel Prize in 1929. Lastly, let me teach you that how can we calculate de Broglie wavelength. For example, calculate the wavelength of a 60-gram ball moving with a speed of 80 meters per second. Well, I write the given data. The mass of the ball is 60 gram. I convert it to kg. I divide it by 1000. I get 0.06 kg. Secondly, the speed of the ball is 80 meters per second. Thirdly, we know that the value of h is 6.626 and to 10 to the power negative 34 joule second. And the de Broglie wavelength is required. We know that P is equal to h upon lambda, or lambda is equal to h upon P. Here the momentum of the ball is mv, so I get lambda is equal to h upon mv. Now I plug in all these values in this equation. After calculation, I get 1.38 and to 10 to the power negative 34 meter. So this is the de Broglie wavelength of the ball, which is extremely small. That's why we cannot detect it. Thus using this equation, we can easily calculate de Broglie wavelength. I hope that you have learned all about de Broglie hypothesis.